I just want to mention a little something. Like I said, I will do a screen recording of this where you hear my voice and you see the screen, so you can always go back to that. I will also put the PDFs of the things I'm going to write here online so you can refer to them. I'm actually teaching from like my own lecture notes here that are essentially it's like rewriting of Griffiths with some additional stuff. And these notes here, so it's the first time I give this course, the notes are not completely converged. However, you know, they're kind of good enough to discuss. And what I will strive to do is to put the PDF of these teaching notes on Canvas on the day of the lecture. Like what I'm going to use now in the coming hour, you can find in the lecture notes folder, okay? And then, so for example, today we're going to talk about electrostatics, and this is in this chapter here. And you'll see I'm kind of trying to organize the notes in a particular way, so you've got some prerequisites, stuff you should know for this chapter, what's the point of this chapter, and then the explanations, okay? And you can see I'm kind of trying to be a bit fancy on these things. You can look at the preface that tells you the legend of the color coding that I'm using. The stuff which is prerequisite stuff. Actually, you don't see the colors very well here, do you? Well, you see the colors in the PDF, yeah? So maybe I'll just darken the colors a bit. But anyway, in the PDF, you'll see there are different colors. Stuff which is important goes in the core material. If something is labeled core, essentially, I'm expecting you to know this stuff by heart, okay? I might not even put these equations in the help sheet for the exam. You're really meant to know this, okay? Stuff which is main material, this is stuff that you should know how to use, okay? But not necessarily know by heart. So for example, the Laplacian in spherical coordinates, I expect you to be able to use it, okay? Whether I really want you to know it by heart is another matter. Okay, so then I would give you that in an exam and things. But I do want you to be able to use it. So that's main stuff. And then the rest is just a normal text. If I do examples, then these are really like applications of the stuff that's just been explained. If I put info, then typically this is stuff that's a little bit to the side. Maybe I'll tell you a little bit more about the Dirac delta function. Maybe I'll tell you a little bit more about some current modifications with quantum field theory you can get for this or that. This is stuff you don't need to pass the course, but which might make it a little bit more fun and entertaining and give you a bit of context. And then also I try to put some historical context in there, because for the case of electrodynamics, it is so interesting. It's just so interesting. There's a lot of it. I haven't put very much yet, but I'll try to put more and more, just so you can put things in perspective and be maybe a little bit impressed that these people all these years ago actually managed to do that. Okay, so that's the idea of the notes. And once again, you know, if you already have your computer with you, you can even just get the notes. Now, that said, I think the practice is really important. So if I write equations here and there, it's much better for your own, you know, brain to copy the equations over and over and over and over again, because then you'll learn them, you'll become familiar with them. So in a sense, you know, ideally you take all these notes. Ideally, you write everything I say in your thing, huh? But then you can see how that goes. Huh? Okay, so let's get started. I mean, today I have like a stupidly ambitious thing which we're not going to be able to meet, but we'll see how far we get. Yeah, we only have a few minutes. So where does it start? Yeah, electrostatics. Two important things, essentially: Coulomb's law, principle of superposition. Okay. I want to insist on proper notation for things. Out of experience, the reason why students struggle with exercises is very often that they use a notation which is not explicit, which is maybe a little bit inappropriate for this. In fact, that holds even for modern research. You'll find that many really, really good researchers they take good notes, they organize their stuff really well, they write unambiguously and things. There's kind of a correlation between that. If you write sloppily, you don't know what you're doing. So I would really encourage, like, taking care of how you write stuff, okay? So here goes. Here's my version of Coulomb's law. So when I say be clear with your notation, I don't mean being legible. Yeah, that's something I can't do, but you'll have to get used to my handwriting, okay? But I assure you, it's an acquired taste, okay? So when I was a student, I used to take good notes, but these days, sometimes I can't even reread myself. So the message I just gave you is mostly for me. But anyway, okay. So Coulomb's law. What does it tell us? It tells us that the force, which is, well, let me just go slowly on this, which is a vector. Okay, what am I doing here? Discuss notation a bit. When I write a wiggly line under an object, I mean it's boldface. Okay? So that means vector. You might prefer if I put a little arrow on top, yeah? That could be a thing. You're welcome to do that. That's great. I write boldface because sometimes I write vectors with a little hat. And then I have one underscript. Anyway, okay? Just, we have to agree on the notation that I use. For vectors, boldface objects, I put a wiggle on it. So the force on a test charge coming from a source charge is equal to the product of the charges, so the Q, which is the charge of the test particle, the charge of the source particle, divided by a number, which is 4 pi epsilon 0. We'll say more about this here. Sorry, my tablet is going crazy. Dismiss. Okay, and you know that it's like 1 over r squared. So how am I going to write this? I'm going to write this in different ways. Very often, I'm going to write the position of the test minus the position of the source. Okay, this is an r. This is my r. This is not Griffiths's r. Okay? Yes, question.
The test thing, is that a C or a T?
That is a T. F, boldface, T. I promise you it gets better, okay? Yes.
Is the R capital or
the R is a small r.
Okay.
I mean, this one. So this little r here is a small r. I'll show you a big R. You want a big R? That's a big R. Okay? Okay, so we carry on. So I've got the distances, and then RT minus RS cubed. Hang on. Yeah? It's 1 over r squared. Why am I writing r cubed? Because there's r on top. Yeah? And the r on top is boldface, so it's a vector. So it's got direction. The one at the bottom has, the one at the bottom just had norm cubed. So this is a scalar. This is the length of the vector difference between position test, position charge. Okay? So, ironically, this is the form that you will see in countless books on electrodynamics. Okay? Because it's giving you the correct vector version of it. Yes?
Wouldn't it be more useful to define a delta R as the vector difference between the two vectors?
It's my next step. I was going to do something like this. Yeah, so you'll see how this way. That's one way of writing it. Okay. I could also say that it's going to be QT QS divided by 4 pi epsilon 0. And now what I'm going to do is somehow get rid of this bloody radial menu. It shouldn't appear. I will simplify the notation by saying it's RTS divided by RTS cubed. Okay? So what I mean by RAB is that it's the difference between the position of the A with the position of the B. Okay? So this is just notation. Okay? So that's typically the way I'm going to write stuff, and hopefully you'll get used to it. Okay, now in the just a couple of discussions, we've already discussed about the exponent in there. We didn't really talk very much about the product here. Of course, it's related to linearity. Linearity tells you that it should be just like that, but it's an experimental fact, right? So this was written like that before. Now, one of the things is that there's this strange number here, this epsilon 0. So this is known as the permittivity of the vacuum, permittivity of free space. It's a number, okay? Now, it's kind of interesting because you might think that these are all constants of nature, but these are related to the systems of units that we use. And we are working with the Système International, SI, International System of Units, okay? And the value of these things depends on what you consider more fundamental than other things. So for example, if you have the speed of light, which is a measurable thing, but you've got the meter and you've got the second. So these are related to each other somehow. So if you have the meter standard in Paris and the second being defined as, you know, so many oscillations of that particular level in the atom, and then you measure the speed of light separately, maybe these things don't go together. So you have to make a choice, okay? So the Système International, the SI, makes choices. It tells you that some things are something. Like it says that the speed of light is a certain number, and then they dictate. That's the number. And the number, yeah, I mean, I really should remember this by heart. It's 299,792,458 meters per second without any inaccuracy. That is the definition of the speed of light. Therefore, we need to adopt either meter or second. Now, the second is also defined as the period of time for God knows how many oscillations of, you know, of a certain level in an atom. Which means that the meter is a derived unit, okay? So, with these things here, there are also things that are derived and fundamental, okay? So, and in the notes, I give you a little info block that explains you these things, okay? So you can just look at that. This is not exam material. It's just so that you know, okay? But just look at it. And interestingly, this was changed in 2019. Okay? They changed one definition, which meant that actually the other constant, which is the permeability of the vacuum that we'll see later when we do magnetic phenomena, this one, its value changed. Okay, but maybe I'll make more comments on that later. Doesn't matter. Okay, so just remember that the kind of force constant for this thing is dependent on the system of units you're using. So if you look at other books, they might use different units. Yeah? Books from the 1960s, from the US, they use a different system of units. They use like, you know, some of the things. Even particle theorists these days, they also use a kind of more convenient system of units where the epsilon 0 is not there. There's just 1 over 4 pi. It's all the same thing, just in different units. Okay?
It's a coincidence that I recognize 4 pi r squared as a factor of the force divided by.
Sorry?
I recognize 4 pi and r squared within its r cubed times, which is r squared times r. So 4 pi r squared, is that a factor by accident or do spheres come into it?
The 4 pi has no fundamental significance. It is absolutely purely conventional. Okay? In some other books, you will see the force being written as Ke with Qt, Qs with the R stuff. And then the Ke is the constant for the Coulomb thing. But yeah, it depends. But we will use this convention here. So for us, it's like 1 over 4 pi epsilon 0. But there is no deep meaning to this. It is just a convention. It's an agreement for the units of measure that we're actually using. Okay? Okay, so then what's important? The principle of superposition. which simply says that the total force on a certain test charge is just going to be the summation over, say you have n source charge. You just sum all these forces. Why does this keep... Okay, so if you want the total force, you just sum up all the forces that that you have in there. So that's the idea of the principle of superposition. Okay, now another thing you know is the fact that you can talk about an electric field. Okay, so the electric field is essentially the force that you feel per unit charge. Okay, so you can rewrite the force that you have on your test charge as the charge of the test charge with the field. And the field, as usual, we will write as a vector. Okay, so this is literally a vector in three-dimensional space, okay, which is a function of the position. So that's this notation here. So E itself is a vector, and it depends on the vector RT, which is the position of the test charge. Okay? Are you kind of getting used to the notation, or is it like that? Well, okay. So this field here, you can just it's just the sum of these things. I mean, so E of R is just equal to 1 over 4 pi epsilon 0 summation I is equal to 1 to n of just what we had. So Qi with then R minus Ri divided by R minus Ri cubed. Okay, sorry, not. Yeah, okay. Okay? So, for example, yeah. So if you have charge Q here and a charge Q here, and you want to find the field at this point here, so let me define this distance as like Z. Okay, and here I will do a distance D between. Okay, so here I've got two charges Q on the x-axis, and I want to know the field on the z-axis, a distance Z from it. Then essentially I can ask myself what it is. So I would have a test charge here. It would feel a force coming from this, a field going this way from this charge. It would feel a field going this way from this charge. By symmetry, essentially, if I'm at the midpoint, the only component of the field that doesn't vanish is the one in the z direction. Okay, so the field that you would have for such a configuration, you can kind of immediately write down. It would be 1 over 4 pi epsilon 0. And then you have 2q times z. And then the distance is really just this z squared plus d over 2 squared. Okay, all of this. Sorry, so the software should not move with my hand. Okay, all of this to the power 3/2 in the direction z. Okay, sorry, the notation is a bit bad. Yeah. This is like 2qz over the distance cubed. Okay, so you just add up the two fields, and then you get a field in the z direction. So that's a simple example. Okay. Now, again, I'm telling you stuff that you've seen before. So if I have continuous charge distributions, again, notations here, when I write this here, so sometimes I kind of cut the word, distributions, okay? Continuous charge distributions. You have different cases for this. So if you have in a volume, you'd have a charge density given to you by a function rho, which would be a function of space. Okay? Then the field that you would feel from a volume charge density would be E of R, would be 1 over 4 pi epsilon 0. And then the integral over the volume, and the notations that we will use will be as follows: d tau prime, rho of r prime, and then again our beloved function r minus r prime divided by r minus r prime cubed. Okay? So again, by superposition, I'm just integrating over all the charges in a certain volume to get the field. Do you recognize these notations from your earlier course? I see gaping mouths and eyes. Yes, question?
I can't quite read the handwriting that well yet, so what exactly does it say in the integral sign?
Okay, I will try to get you used to it. Okay, integral, so 1 over 4 pi epsilon 0, that one you know. Integral over a certain volume. So here I'm thinking that I've got like a certain volume in 3 space. Okay, that's my V. And I've got a rho, I've got a charge density in here, right? So these are all charges here. And the charges have a density. Okay, so integral over the volume of d tau. Tau is the volume element in this. If you're using Cartesian coordinates, d tau is dx, dy, dz. Okay? So it's the differential volume element. And then I have rho of r prime, which is the density of charges per unit volume at that point in space, at r prime. And then each of these contributes to the field with the canonical, 1 over r squared vectored function. Okay?
Integral notation of ambiguous. You define the d tau, and then you define what you are integrating. If it's in the middle of a long line, you don't know where to stop integrating.
So these are different conventions. For me, I like to put the differential element next to the integral that it pertains. And if there is anything that depends on the variables being integrated, it is to the right. Okay, with multiple integrals, sometimes you can't make it completely unambiguous, and then typically I would write parentheses around things. But my order is, so some authors put the differential element on the other side, and then you have everything between the integral and the differential element. If you have multiple integrals, sometimes it kind of goes from outside to the inside. I'd rather read it left to right. Purely conventional. You're welcome to use a different convention. I am just telling you the convention I'm using. Okay? It's like usual with conventions, the important thing is that you are consistent with yourself. I'm trying to do that. Yes?
Should it be d tau or d tau prime?
So, here the kind of convention is that I use primed variables for integrating over source charges. Okay? So here I want to know the field at a point r in space, which is completely arbitrary. And my sources are distributed within a volume V that I coordinate with r prime, that I integrate over this volume. Okay? Sometimes I kind of cut the prime when there's no ambiguity, but typically I will try to systematically use primed variables for source things. Okay? I mean, but sometimes I don't. So, yeah.
You're integrating over tau prime, and in the integral you use the variable r prime. How do these two relate? Are they the same? Or?
So r prime would be, for example, x, y, z, and d tau prime would be, or you know, x prime, y prime, z prime. That's r prime. And d tau prime is dx prime, dy prime, dz prime.
Okay.
Yeah? But I'm not specifying the coordinate system I'm using here. Okay? Because I could use spherical if I wanted to. I could use hyperbolic coordinates if I wanted to. The expression doesn't change. Okay? So that's the version for continuous charge distributions. Okay? I could have essentially also for surface charges. With surface charge density that we'll denote as sigma. Okay, sigma is now a density of charge per unit area. Okay. Then if I have a surface distribution, then my my field E of R would just be 1 over 4 pi epsilon 0. And now I would do a surface integral. So this is now over a surface. And I will write the differential element as dA prime, sigma of R prime. And again, as usual, as always, R minus R prime. Yes, as always, the little jump. Okay? Am I right that you've already worked with these expressions? That you've computed fields for disks and things like that, so you know what this is, right? So now dA prime, if I'm coordinating my surface by x and y coordinates, or x prime and y prime coordinates, dA prime is just dx prime, dy prime, right? Whatever coordinates you want, okay? And then finally, if I have for line charges, with a line density lambda of R prime, or you know, lambda of R, lambda R prime, then my field at R is just now the integral over a certain path. Okay, and then dl prime with lambda of R prime, and again R minus R prime divided by R minus R prime cubed. Okay, and now so L prime here coordinates the path that I'm taking. Okay, so depending on your path, for example, if you had an arc of a circle, okay, then this dl prime would be the line element along this path on the circle. Or if it's the side of a square, then it's just, you know, the differential element coordinating you the path going through this. Okay? So I presume you've kind of seen these things before. Yeah? Okay. So one example. Let's do a quick example. Okay, so find E above the midpoint of a segment of length 2L with line charge density lambda. Okay, so how does this look? I have my line. It's a straight line, yeah, completely straight. It has length 2L, and I want to know the field midway at a certain height z in the z direction. Okay, and here that would be, for example, the x direction. Okay, again, little notations. So here, what do I mean? I delineate the ends. Yeah, so this is like a barrier left, barrier right. 2L distance between these 2 points. X hat is the unit vector in direction x. Z hat is the unit vector in direction z. Z is my height above the midpoint of this line. Okay, so how do I calculate this? So conventions. The position that I have, so R, if you want, the place at which I want to know the field is just going to be some number z in the z direction. Okay. The R prime, which is my source position, my position along this, this is going to be just some number x in the x direction. Okay. And then my R minus R prime is just the distance between the point where I'm at and here. So it's just given to me by z squared plus x squared, okay, square root, right? So now I will apply my formula. I will calculate the field at R. And I remind you that R is just z times the unit vector in the z direction. So what is this? This is 1 over 4 pi epsilon 0. Integral now from minus L to L dx prime. Yeah, here I guess I can even drop the prime because I can. Drop part of the x as well. Of what? Yeah, so I've got the line density lambda, which is a constant along this thing, so we'll be able to take it out of the integral. But I've got r minus r prime, so this is z hat minus x hat divided by the length cubed. So this is just z squared plus x squared to the power 3/2. Okay, so now we just need to do the integrals. Let me start with the integral coming from the second term here, because it's easy, because it is an integral over a symmetric interval in x of a function which is odd in x. Therefore, this term here integrates to 0, and I only need to consider the first term. Okay? I can take the z and the lambda out because it's they're not dependent on x. So what this is really I have the lambda times z over 4 pi epsilon 0. The z is just a direction, so I can write it wherever I want. But now I have the integral from minus L to L dx of 1 over z squared plus x squared to the power 3/2. Okay, so I mean this is just an integral. I'll just give you the answer. So nota bene, you have that dx of x divided by z squared plus x squared square root what's this equal to? Let me write it here. Don't know why it does this. So what is this? I differentiate with respect to x, so I've got 1 over the square root minus, then I need to differentiate with respect to the x here. I've got 1 over square root. Yes, I've got a minus a half, and then the thing to the power 3/2. But then I need to differentiate the x squared here, which gives me 2x. So that means that there's an extra x squared with the thing here to the power 3/2. Okay, and if you just do the simple algebra for this, I can just recombine these two things. So that just gives me z squared divided by z squared plus x squared to the power 3/2.